Hello, I'm going to do the last three problems from this practice test. Let's see what we got here. Some pencil underneath my paper. It's the wrong way around. An ideal spring with spring constant K is cut in half. What is the spring constant of either one of the two half springs? Not really something that we ever talked about. So, what is going to happen if we cut the spring in half? Well, if you hung a mass M, well, let's say you just apply a force F to this, then I know for the whole spring F is equal to Kx. And that's like for the whole spring. So what is the spring constant going to be if I cut it in half? Well, if I cut it in half, then for that half spring, if I have the same amount of force, then that is going to displace the spring by half as much, because if we look at the whole displacement of this, if this was like the equilibrium position and that's where it got displaced to, then half the spring only displaces half as much. So the K here, I know that this is true, right? So the K here would have to be 2K. Would be the spring constant for half of it. Well, that's a little tricky, but basically like a proportional reasoning kind of situation there. The same amount of force is only going to displace it this much, so that means that the spring constant is twice as much. All right, number 34. A rocket has landed on planet X, which is half the radius of the Earth. An astronaut on board the rocket weighs twice as much on the planet X as on Earth. If the escape velocity for the rocket taking off from Earth is v sub 0, then its escape velocity on planet X is... Okay, so escape velocity, you can derive that using energy considerations. If you want to go back and look, there's some notes in the middle of Unit 13 that go through that escape velocity. It's not on the formula sheet, but it's a good idea to know what it is, and that it is the square root of 2 gm over r. So this astronaut weighs twice as much on planet X as they do on Earth. So I'm going to leave that for a minute and say, so force of gravity on Earth is equal to g m over r squared, right? And what they're saying is that on planet X here has half the radius, so if you plug in half r for this, that's going to make it increase by a factor of 4, right? Putting a 1/2 and squaring it on the bottom of this. And the astronaut only weighs twice as much. So that means the mass of the planet, of course the mass of the astronaut is the same thing, the mass of the planet must be half the mass of the Earth, right? Because this, having that, is going to increase this by 4, but they're saying that his weight, an astronaut, look at that, it's, her weight is only twice as much. So there must be a factor of 1/2 in here. Of course, that's universal constant. This is the mass of the astronaut. So this must be half, because having this is going to increase it by a factor of 4, so we must have half that. So mass of planet X equals the mass of the Earth over 2. So now I think that we know what we need to know to do this. So more proportional reasoning, what is going to happen if I introduce into the formula for escape velocity, what if I have this, dang it, it's 2 times the mass of the Earth. And this is half, right? So what happens if I double this and then I have this? Right? Isn't that what we're talking about? I'm going to double this, and then I'm going to have this. Hold on a sec. No, this was right, that it was half. Jeez Louise. I was right the first time here, because this is going to increase it by a factor of 4, so that must also be half. So if I put a half here and a half here, those two things are going to cancel each other out, and we're going to get the same escape velocity as we have on Earth. So again, sorry for the confusion there. Because having this quadruples, and we know that astronaut only weighs twice as much, this must be half m. And then when I look at the proportional reasoning here, if I put a half here and a half here, cancels out and you get the same thing. So the correct answer is C. All right, last one. So here, this is a tricky question, I think. It's the last one. Sometimes they save tricky ones for last. Sometimes they don't. So if we want to know how fast this thing is going when it gets to here, you can't really do it using conservation of energy techniques, because at the center of an object are universal gravitational potential energy, negative GMM over R, like that fails at the middle. Like our separation, when we have infinite separation, that's where it's 0, and then it decreases to negative infinity. So we can't really use that. It fails when R is 0. So what do we do? And this is only for like not being like inside of an object. Also, this is like for two like objects that are separated from each other. So this does not apply here on the inside of the object. But we do know, and we have seen, that the force of gravity inside of a sphere looks like this, and then it starts to fall off and do the inverse square thing here. So if you want to know, this is a force versus position graph. So how much work does this gravitational force do as this drops from here to here? Well, it does this much work, right? Because work is equal to the integral of force with respect to r, so it's just the area of this. And I know that right at r, like right at the surface, that amount of force is GMM over r squared. So what's the area of this triangle that is r wide and GMM over r squared high? Well, it's 1/2 times GMM over r squared times r. So that gives me this expression right here. And if you picked 3 only, I wouldn't feel too bad about yourself. These ones, when you look at the lowercase g, you might think to yourself, well, what the heck does lowercase g have anything to do with this? Well, I'll tell you. We know that the force of gravity at the surface of the Earth is mg. But we also know that the force of gravity anywhere is g, sorry, my pen's broken, GMM over r squared. So our lowercase g for the particular m that is the Earth and the particular radius that is at the Earth's surface is equal to GM over r squared. And that gives us another way of writing this expression here. So I'm going to look at this. I'm glad I didn't simplify this, because there's the gm over r squared right here that is equal to lowercase g. So 1/2 g times little m times r is also equivalent to that. And that's pretty tricky to recognize that, I think. So the correct answer is E.